Good morning everyone. The topic of my presentation is dephosphorization of ferromanganese alloy. Contents of the presentation. Ferroalloys are one of the important inputs in manufacturing of alloy and special steel. The growth of ferroalloy industry is thus linked with iron and steel industry and foundry industry. Manganese, chromium and silicon are common ferroalloys. Industrial production and consumption. In India, 5.1 million tons of bulk ferroalloys and 50,000 tons of novel ferroalloys are produced per annum, in which ferromanganese constitutes almost half of the total production. But low phosphorus ores are depleting fast, and high carbon ferromanganese products will continue to have phosphorus more than 0.4%. Objective. In the view of difficulties, a systematic study was taken up to remove phosphorus from high carbon ferromanganese under oxidizing condition using barium oxide based flux pellets, and also optimize the flux consumption to make the process economical. The role of oxygen potential and each component of the flux pellets. Effect of oxidizing condition. Increasing oxygen partial pressure favor dephosphorization but also increases the manganese loss. Therefore, dephosphorization is required to be carried out at relatively low oxygen potential. Effect of barium oxide. It increases the basicity of the slag. High basicity help us to carry out dephosphorization within a narrow range of oxygen potential. Effect of barium fluoride. It facilitates melting of pellets at moderate temperature. It also increases the fluidity of the slag and activity of manganese oxide. Effect of manganese oxide. The addition of manganese oxide acts as a source of oxygen in the bath for oxidation of phosphorus. Experimental procedure. The dephosphorization tests were carried out in a medium frequency induction furnace at moderate temperature under oxidizing condition. Different portions of barium carbonate, barium fluoride and manganese oxide were selected for the preparation of green pellets, which is calcined at 1050 to 1100 degrees centigrade for 1 hour, and a master alloy of homogeneous composition was prepared for use in each test, and following parameters were studied: types of flux, quantity of flux, effect of temperature and time. Result and discussion. Type of flux. Initial test in test number 1 and 2 were carried out using calcined flux pellets with 10% flux weight in the temperature range of 1350 to 1370. There was significant phosphorus removal from 57 to 61%, but manganese loss was extremely high. In order to reduce the manganese loss, additional manganese oxide in the flux was considered. It was observed that melting barium oxide based flux was possible at 1350 degrees centigrade when the manganese content was 10%, which facilitates 59% phosphorus removal and also reduced manganese loss less than 2%. However, when manganese oxide was increased to 20% in the flux, poor dephosphorization occurs. Therefore, flux composition consists of 54% barium oxide, 21% barium fluoride and 10% manganese oxide was selected for conducting subsequent tests to study the effect of other parameters. Quantity of flux. These tests were carried out to study the effect of change in flux quantity on the degree of dephosphorization. The flux weight was varied from 15% to 2.5% of the alloy weight. To increase the extent of phosphorus removal, the flux weight was first increased from 10% to 15%, but there was no significant improvement in phosphorus removal. The flux quantity was then reduced to 5% while using improved mode of addition. The results show a 63% phosphorus removal but manganese loss of 3.5%. In the next test, the flux consumption was further reduced to 2.5% using same mode of addition. However, only 40% phosphorus was removed, indicating that 5% barium oxide based flux is the optimum weight for more than 60% phosphorus removal. The effect of temperature on the degree of dephosphorization and manganese loss. On the basis of result obtained at different temperature, it appears that the degree of dephosphorization appears to reach maximum at about 1400 degrees centigrade. This may be due to the fact that oxygen partial pressure at slag metal interface for a fixed slag composition increases with the temperature and the phosphate capacity of the flux decreases with the increasing temperature. This table also shows the effect of change in temperature on manganese loss. The manganese loss was 2 to 3% when the temperature was below 1400 degrees centigrade and was reduced to almost nil when the temperature was increased to 1450 degrees centigrade. Effect of residence time. It was observed that lower temperature requires longer residence time for the pellets for better phosphorus removal. Sample collected after 10 to 15 minutes of the addition of flux have shown adequate phosphorus distribution ratio in the temperature range of 1350 to 1450 degrees centigrade. It was also observed that temperature in the range of 1450 degrees centigrade, the phosphorus distribution approaches a stable value within 10 minutes, and after that there was no significant change in phosphorus removal. Conclusion: developed process at laboratory scale shows selective removal of more than 60% phosphorus from high carbon ferromanganese melt with the use of barium oxide based flux. 10% manganese oxide was found to be most suitable for melting the flux at moderate temperature between 13 to 1400 degrees centigrade for maximum phosphorus removal. The process restricts the manganese loss to less than 2 to 3%. The drop in temperature in liquid ferromanganese after the addition of barium oxide based flux was not significant. Therefore, it may be possible to use these flux pellets for the treatment of liquid metal in the ladle after the metal is tapped. Reference. Thank you.